Imagine a water droplet whose initial mass is 1. At one instant, an impact removes a small portion of mass. Call that lost portion x, so the mass that remains is not 1 anymore. It is 1 minus x. Now compare the original droplet with what remains after the impact. The expansion factor is the original mass divided by the remaining mass. So alpha equals m0 over m1. Since m0 is 1 and m1 is 1 minus x, alpha equals 1 over 1 minus x. This is why the quantity is larger than 1. For example, if x is 0.2, then 1 minus x is 0.8, and 1 divided by 0.8 is 1.25, so the ratio has expanded. Before the impact, the droplet may fluctuate a little. A tiny loss, followed by an equal tiny gain, changes nothing overall. Minus epsilon plus epsilon is 0, so the meaning of alpha does not change. We still have alpha equals 1 over 1 minus x. Now the key step becomes visible. One can rewrite the numerator as 1 minus x plus x. This separates the ratio into two parts. The first part is 1. The second part is x times alpha. Therefore, alpha equals 1 plus x alpha. And this is the beginning of the recursion. We ended with a strange equation. Alpha equals 1 plus x times alpha. The same quantity, alpha, appears again on the right. That is the important clue. If alpha equals 1 plus x alpha, then the alpha on the right can be replaced by the same expression. So alpha becomes 1 plus x times 1 plus x alpha. Now distribute the x. The first term is 1. The second term is x. And what remains is x squared times alpha. So alpha equals 1 plus x squared alpha. But the process has not stopped. There is still an alpha at the end, so we replace that alpha again. Now the expression becomes 1 plus x squared plus x cubed alpha, and again, 1 plus x squared plus x cubed plus x to the fourth times alpha. Every step creates one new visible term. The remaining unknown part is pushed to a higher power of x. Since x is between 0 and 1, those powers become smaller and smaller, so the tail becomes less and less important. What remains is the geometric series. Alpha equals 1 plus x squared plus x cubed plus x to the fourth, and so on. This is the same expansion factor, now seen as a sum of smaller and smaller effects. Now we make the bridge from the expansion of alpha to Taylor series. The important pattern is this. A quantity can be written as powers of x. 1, x squared, x cubed, and so on. To see that this is not mysterious, take a familiar function. F of x equals x squared plus 2x plus 1. This is just a parabola. Now write the same function starting from the lowest power of x. First the constant term, 1, then the first power, 2x, then the second power, x squared. The function has not changed. Only our point of view has changed. Now ask, where would the next powers go? X cubed, x to the fourth, x to the fifth. For this parabola, those coefficients are 0, so we can write the same function as 1 plus 2x plus x squared plus 0x cubed plus 0x to the fourth, and so on. This is the bridge. A polynomial is already a power series. It is a power series that becomes silent after a finite number of terms. Now replace the specific coefficients by names. The constant coefficient is a sub-0. The coefficient of x is a sub-1. The coefficient of x squared is a sub-2. Then come a sub-3, a sub-4, and so on. So a general function, if it can be expanded this way, has the form f of x equals a sub-0 plus a sub-1x plus a sub-2x squared plus a sub-3x cubed plus a sub-4x to the fourth, and so on. Now the real question is clear. How do we find those coefficients? In the next step, derivatives will extract them. We ended with the general power series. F of x equals a sub-0 plus a sub-1x plus a sub-2x squared plus a sub-3x cubed, and so on. Now the question is, how do we find the coefficients? Start with the easiest one. Put x equal to 0. Every term that contains x becomes 0. A sub-1 times 0 is 0. A sub-2 times 0 squared is 0. A sub-3 times 0 cubed is 0. Only the constant term survives. So f of 0 equals a sub-0. That gives the first coefficient. Now we need a way to make the next coefficient become the constant term. This is what the derivative does. Differentiate term by term. The constant, a sub 0, disappears. A sub 1x becomes a sub 1. A sub 2x squared becomes 2 a sub 2x. A sub 3x cubed becomes 3 a sub 3x squared. So the first derivative is f prime of x equals a sub 1 plus 2 a sub 2x plus 3 a sub 3x squared plus 4 a sub 4x cubed, and so on. Now put x equal to 0 again. Every term that still contains x disappears. Only a sub 1 remains, so f prime of 0 equals a sub 1. That gives the second coefficient. Now do it again. Differentiate the first derivative. The term a sub 1 disappears. 2 a sub 2x becomes 2 a sub 2. 3 a sub 3x squared becomes 6 a sub 3x. 4 a sub 4x cubed becomes 12 a sub 4x squared. So f double prime of x equals 2 a sub 2 plus 6 a sub 3x plus 12 a sub 4x squared, and so on. Put x equal to 0. Only 2 a sub 2 remains, so f double prime of 0 equals 2 a sub 2. Since 2 is 2 factorial, we get a sub 2 equals f double prime of 0 divided by 2 factorial. The same pattern continues. The third derivative at 0 gives 6 a sub 3, and 6 is 3 factorial. The fourth derivative at 0 gives 24 a sub 4, and 24 is 4 factorial. So, in general, the nth derivative at 0 equals n factorial times a sub n. Now solve for the coefficient. A sub n equals the nth derivative of f at 0 divided by n factorial. This is the mechanism. Derivatives do not magically create the Taylor series. They measure the local behavior of the function, one order at a time. When we put those coefficients back into the power series, the Maclaurin series appears. Now we have the Maclaurin formula, but a formula is not yet understanding, so let us see what it does. Take the function e to the x. This is a perfect first example because every derivative of e to the x is again e to the x. At x equals 0, e to the 0 is 1, so the value is 1. The slope is 1. The curvature information is also 1, and the next derivative information is 1 again. For this function, all the derivative measurements at 0 are equal to 1. Therefore, the Maclaurin series becomes e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, and so on. Now do not jump to infinity. Build the approximation one piece at a time. The 0th approximation is just 1. It only knows the height of the function at 0. The first approximation is 1 plus x. Now it also knows the slope at 0. The second approximation adds x squared over 2 factorial. Now it starts to bend. The third approximation adds x cubed over 3 factorial. The fourth adds x to the fourth over 4 factorial. Each new term adds one more order of local information. On the graph, the blue curve is the real e to the x. The approximating curve begins very simple. Then it bends more like the real curve. The improvement happens near 0 first because all the measurements came from 0. Farther away, the approximation needs more terms. At x equals 1, we can see the numbers approaching e. P0 gives 1, P1 gives 2, P2 gives 2.5, P3 gives about 2.667, P4 gives about 2.708. The real value is about 2.718. So the picture and the numbers say the same thing. A Maclaurin polynomial is a local model. It turns derivative information at 0 into a function that imitates the original function near 0. Maclaurin has one limitation built into its notation. Every measurement is taken at 0. The height is f of 0. The slope is f prime of 0. The curvature comes from f double prime of 0. And the power x to the n is really x minus 0 raised to the n. So Maclaurin is a Taylor series whose center is 0. But 0 is not special because of the mathematics. 0 is special only because we chose it as the center of observation. If the interesting part of the function is somewhere else, we move the center. Call the new center a. Now the question is not, how far is x from 0? The question becomes, how far is x from a? That distance is x minus a. This single replacement is the geometric reason for the term x minus a in Taylor's formula. The second replacement is about measurements. If the center is no longer 0, we should not measure the height, slope, and curvature at 0. We measure them at a, so f of 0 becomes f of a. f prime of 0 becomes f prime of a, f double prime of 0 becomes f double prime of a. The same coefficient mechanism from Maclaurin still works, only the center has moved. Now watch the graph. The blue curve is the original function. The yellow point is the new center A. The first local model only knows the height at a, that is P0. The next model also knows the slope at a, that is the tangent line, P1. The next model also knows curvature at a, that is P2. Near A, the local model imitates the real function. Far from A, it may stop being accurate because the information was collected locally. So the Taylor series is not a different idea from Maclaurin. It is the same idea, with the microscope moved from 0 to A. Maclaurin is the special case A equals 0. Taylor is the general version. And this is exactly the tool we need before applying the method to physics. Now we use the Taylor machine on a real physical formula. In special relativity, one of the central quantities is the Lorentz factor. Gamma of beta equals 1 divided by the square root of 1 minus beta squared. Here beta is not a new speed. It is the ratio v divided by c. So beta tells us how large the object's speed is compared with the speed of light. If beta is close to 0, the object is moving much slower than light. That is exactly the Newtonian regime. So the question becomes, what does the relativistic gamma function look like near beta equals 0? This is a Maclaurin question. We take the function gamma of beta and we expand it around beta equals 0. First, gamma of 0 is 1. Physically, at 0 velocity, the Lorentz factor is 1. Next, the first derivative at 0 is 0. That means there is no linear correction. The graph is symmetric around beta equals 0, so the first change cannot be proportional to beta. The second derivative at 0 is 1, so the first non-zero correction is beta squared divided by 2 factorial. The third derivative at 0 is 0 again. Now the fourth derivative is the place where we must be careful. The correct fourth derivative contains the term 24 beta squared in the numerator. When we put beta equal to 0, the fourth derivative gives 9. So the beta to the fourth coefficient is not 1/8. It is 9 divided by 4 factorial. Since 4 factorial is 24, this becomes 3/8. Therefore, the Maclaurin expansion is gamma of beta equals 1 plus 1/2 beta squared plus 3/8 beta to the fourth, and so on. Now we use the physical assumption. For ordinary speeds, v is much smaller than c, so beta is very small. If beta is small, beta squared is already tiny. Beta to the fourth is even smaller. So for the low-speed approximation, we keep only the first correction. Gamma is approximately 1 plus 1/2 beta squared, and because beta equals v divided by c, this becomes gamma is approximately 1 plus 1/2 v squared over c squared. Now insert this into the relativistic energy. The total relativistic energy is E equals gamma times m sub 0 times c squared. At rest, gamma equals 1, so the first term is m sub 0 c squared. That is the rest energy. For low speed, replace gamma with the approximation we just found. E is approximately open parenthesis 1 plus 1/2 v squared over c squared close parenthesis times m sub 0 c squared. Now distribute. The one gives m sub 0 c squared. The second term gives 1/2 times v squared over c squared times m sub 0 c squared. The c squared cancels. What remains is 1/2 m sub 0 v squared, so the low-speed energy becomes m sub 0 c squared plus 1/2 m sub 0 v squared, and the second term is exactly Newton's kinetic energy. This is the point. Newtonian mechanics is not thrown away by relativity. It appears inside relativity as the low-speed Taylor approximation. Taylor series does not merely approximate a formula. Here it connects two theories. So what is an approximation of? Not of reality itself. It is an approximation of a more general description inside a specific regime. This is the practical meaning of Taylor series. A Taylor series does not say, the world is fake. It says, near this point under these conditions, this simpler model is what the deeper law looks like. That is why the center matters. Around 0, Maclaurin gives a local model. Around a different point, Taylor gives a different local model. The model is useful when we stay inside the neighborhood where its terms remain small in the right order. In physics, this becomes a powerful idea. For the Lorentz factor, beta equals v divided by c. When beta is close to 0, the relativistic series becomes 1 plus 1/2 beta squared plus smaller terms. In that low-speed regime, the energy becomes rest energy plus Newtonian kinetic energy. So Newtonian mechanics is not simply wrong. It is the low-speed face of relativity. It is a local truth, but a local truth has a range. If the speed becomes comparable with the speed of light, beta is no longer small. Then the higher terms are no longer negligible. The approximation is no longer enough. The full relativistic formula must return. The same lesson appears in energy. In everyday motion, like a car moving along a road, we mostly notice the kinetic term, 1/2 mv squared. In nuclear processes, like the energy produced inside a star, changes in mass reveal another part of the same structure, delta E equals delta mc squared. Different regimes make different terms visible. That is the real lesson. A simpler theory can be excellent without being final. It can be the local form of a deeper theory. Taylor series gives us a mathematical bridge between those levels. It tells us not only how to approximate, it tells us why an approximation works when it works and when we must move beyond it. So the world we experience every day is not false. It is local. It is the part of a deeper structure that becomes visible in our regime. And understanding a theory means knowing its formula, its regime, and its limits.